at leisure. I'm not just going to read this. So the basics of any solid combustion fuel device, typically we require a solid fuel composition. So from the first principle, I can calculate the calorific value of that particular fuel. You would require approximate and ultimate analysis of the fuel. Then I need to understand the theory of combustion, which is essentially the oxidation reactions of various components which are present in that biomass. I need to understand whether I am burning a single particle or, as in the case of a fuel, where I have a packed bed of particles. What are the ignition methods which I should use? Should I light it from the bottom or should I light it from the top? And I'll explain it to you why this is so important. It appears trivial, right? But it has a huge implications in terms of the efficiencies. So I do a approximate analysis and ultimate analysis. It tells me how much of carbon is there, how much of total volatile matters is there, how much is fixed carbon there, what hydrogen, nitrogen, oxygen, sulfur, ash, so on and so forth. So this is all available, and I don't have to do these experiments, the standard biomass composition which is available. I just want you to have a look at these two small videos, and I'll explain it to you in a minute. You see the top video where a single particle is being burnt, and you see how the combustion goes on. And here in this particular case, a bed of these particles is being burnt. What you see here and what you see here, just observe it. The flame is going up. You see the piece of wood is not held vertical. It is kept at an angle. I'll tell you the reason for that. If you can tell me the reason, I'll be more than happy. You look at this particular portion, the combustion front is moving in the downward direction till a complete devolatilization occurs. And here you see after the combustion is over, if I start blowing the air, the material gets completely oxidized. Now can anyone tell me why do you think that piece of wood particle was kept at an inclination and not just kept vertical? Anyone? Which is released by combustion must be transferred to the part of the wood which is not combusted. It should raise its temperature to its auto ignition temperature, and then only the combustion process will continue.
It is the trench effect?
Sorry?
Trench effect?
What is trench effect?
Because this is the same principle they have used for an accidental accident.
It's possible. I am not aware of that. But the basic thing I have to know is when the heat is being released as a result of combustion, the heat is being transferred by convection, the heat is being transferred by conduction, and the heat is being transferred by radiation. In the case of this device out here, the air is moving from bottom to top. Correct? So the heat which is released at any of these ignition fronts is being carried in the upward direction because of the convection. Now if it carries in the upward direction, how will the lower portion, which is still not combusted, will get heat? Conduction of biomass, thermal conductivity of biomass is very poor. So it cannot get heated up. The only possibility for it to get heated up is because of radiation. Radiation doesn't need any medium. So if I have got a hot surface, then some part of energy associated with that hot surface will radiate in the downward direction, and if that energy is sufficient to raise the temperature of the lower part, unburned part, to its ignition temperature, the ignition front will keep on moving in the downward direction. Right? That's the reason why this is inclined. So part of the convective heat is being transferred in the upward direction and the process continues to burn. This is also supposed to run, but anyway. So this just I am trying to indicate here, if I light it from the bottom, if I lit it from the bottom, if I lit it from the top. If I lit it from the bottom, the volatiles have come out because of the increase in the temperature, and the volatiles go out. Volatiles don't have any air to combust, and that is why the material or this starts smoking. The moment you start lighting it from the top, the volatiles are combusting at the top. The volatiles are getting released as a result of propagation of the combustion front, and these volatiles go up where they see a flame, where the air is there, and they will start combusting it, and you will have a completely smokeless combustion if you light it from the top rather than lighting it from the bottom. The bottom lit stoves will always produce a lot of smoke, and if you put a light out here, if you put a matchstick out here, you will find that these volatiles will burn, but you will require a secondary air. That means you require primary air to devolatilize, and you require secondary air to combust this volatile mass. So once you have understood these basic processes, the next thing is essentially to start looking into writing the basic material energy balance equation in terms of the model equations which are necessary. What parameters can be estimated? The effective flame temperature and as a function of excess air. People are aware of the concept of adiabatic flame temperature, second year in case of chemical engineering student, or adiabatic flame temperature. If I am supplying a stoichiometric quantity of oxygen which is required to combust a fuel, then the entire fuel as well as the associated flue gas will reach some maximum temperature. That particular temperature is just an energy balance. The heat released and the released heat is being utilized for raising the temperature of the flue gases. You have seen a gas burner. What is the color of the gas burner flame do you get? Blue. What are the typical temperatures of these gas burner flames? About 1100 to 1200 degrees centigrade. Right? Whereas if you go and see a solid fuel burning stove, what is the typical flame color you get? Either it is yellow or yellow and orange type of flame, and sometimes it smokes, sometimes it doesn't, which clearly indicates that the heat which is being released is not being effectively utilized. Because if it was effectively utilized, then I would get a blue flame also from a solid fuel burning stove, and the temperature of that blue flame should also be in the range of 1100 to 1200 degrees centigrade, as against about 700 to 800 degrees centigrade which I get in a conventional solid fuel burning stove. Okay, I will tell you. So our objective is to devise or to design a stove which essentially produces a blue flame, right? And how it can be done, we will explain it in a minute. So I can understand the adiabatic flame temperature, the air suction which is required for continuation and the sustenance of a flame. What is the rate at which the ignition front is moving down? What is the heterogeneous combustion model where the char which is in the solid form starts combusting from the surface? And I can put all this in some sort of a graphical user interface like your Excel sheet where you plug in numbers and you can get all the design parameters. Indeed, that's exactly what has been done. So this is a steady state energy balance equation, so I am not going to spend a lot of time on this equation, but what I am teaching you is going back to the slide of material energy balance. So I have just written an equation for energy balance, that's it. Okay? And if I see the effective flame temperature versus the excess air, as the excess air increases, more heat is being utilized to raise the temperature of that additional quantity of air which is added, as a result of which the effective flame temperature starts going down. So from about 1800 degrees centigrade, it can go down to as low as 800 degrees centigrade, depending upon how much excess air is being utilized. What is the disadvantage? The moment I use excess air to ensure that the combustion is complete and nothing is remaining unburned, that excess air will also lower the temperature of the flame. If it lowers the temperature of the flame, the radiation being proportional to T to the power 4, the radiation front will move slowly. If it moves slowly, I will not get a sustained combustion. So I have to have a balance of all this to to obtain a sustained combustion process. Second year, third year people would have known or have used Ergun's equation. Right? Essentially, this is a chimney effect. You have a hot bed here of fuel and a hot column of air. You have a cold column of air. The hydrostatic head between these two exists. So the cold fluid, which is cold air, will start moving towards the hot fluid because of the pressure gradient which is present in it. But how do I get this hot bed first? I need to light it first. If I light it and then establish a flame, then only the suction is going to be possible. So you may require a forced suction to start with, but once the flame is established, it is not necessary for me to continue to supply air. The air will start getting sucked as and when which is required. So I can write this and obtain the extent of suction of the pressure driving force which is generated, and this pressure driving force then can be utilized to estimate the quantum of burning capability which is there. Right, so I get a flame temperature of 600 or 800 depending upon how tall the bed height is. It's equivalent if I want to have a large suction, I use a taller chimney, correct? So the pressure differential increases. Same case here, if I have a tall bed, but if I am having a tall bed, there is another disadvantage. What is the disadvantage? The flame front, when it reaches the bottom of the tall bed, I am making Birbal's khichdi. The pot is somewhere here and I have got flame which is at a distance of 2 meters, 3 meters, and I have to wait till long. If I have a mechanism by which all that heat energy released can be so stored and can be transferred in a unidirection, then only it is possible. So I have to have some limit in terms of what is the bed height which I can use. Alright, so these are typical conditions. So I have a fuel bed, I light it from the top, devolatilized and only char is left. This is the ignition front which keeps on moving in the downward direction. This is unreacted fuel and air is being introduced from the bottom. Right, I can write a basic material balance of this, and then this material balance can be combined with the calorific value of the fuel to write an energy balance across this particular cross section of the fuel bed. Right, so I can estimate the ignition front velocity by using this particular balance. So the ignition front velocity can be used for the determination of burn rate and power delivery. Right, depending upon the size of your vessel, you choose a larger flame or a smaller flame depending upon by adjusting the flame temperature, correct? Whether I want to use a larger burner or a smaller burner, I adjust it accordingly. And similarly, I should have that flexibility in the solid fuel burning stove to be able to control the energy delivery, and that can be done by adjusting the cross-sectional area and the flame front velocity or ignition front velocity and adjust it accordingly. So these are the typical values which you estimate for one specific quantity, and what you see here, if the initial moisture content is higher, the propagation velocity is lowered. Why is that? Because that needs to be devolatilized, because till the moisture is there, it will not reach the auto ignition temperature. Only after removal of moisture, the auto ignition temperature will be reached. So this is the basic schematic of the model. So you have secondary air from the annulus, primary air introduced at the bottom, and you have a combustion front at this, you have a vessel on top. I will show you some photograph. So we make these assumptions as any chemical engineers do, and the 4 successive steps are modeled. Evaporation of moisture, devolatilization of pyrolysis, homogeneous combustion, heterogeneous combustion, as is occurring in this. So I can write the model equations for gas phase continuity equation, gas phase energy equation,